In this demonstration, we're going to explore how overlay components work in roadway corridor modeling of open roads technology and explain some of those terms and take a look at a few typical examples in the ways overlay is generally constructed as well as milling in our real construction project. So the first thing I want to take a look at is just the basic screenshot of an overlay component and point out that there are some additional properties that we add to be able to assign the component controls over the top and bottom independently. For example, on an overlay component, we have an option for the top of the component and for the bottom of the component. The top will have the ability to follow component, and that is one particular term that you may find confusing. Another way to think of follow component means to follow what you draw. So just remember, I want to follow what I drew originally when I created the component itself. So for example, if I drew 12 feet at minus 2%, that is what I want the top to follow, the 12 feet at minus 2%. We also have the ability to follow the active surface, and we can follow the highest or the lowest of the two. And the active surface typically is your existing ground. Doesn't have to be, but it usually is. And then we can repeat those same scenarios then for the bottom, and we'll get into these examples in a moment. Then we also have depth below component, and that is measured from our proposed profile PGL location. Typically, that's a way that we can force a particular bottom of milling or bottom of leveling binder location. Basically, though, the component depth means wherever you set that component based on a profile, and let's say we have a PGL located 12 feet at 2% minus, then it'll follow that down, basically parallel, whatever depth you set below the top of the component. The other option is that we can follow the active surface or a specified surface name, and that simply parallels that active surface if you give it a depth. Let's take a look here then, a couple more slides before we get into an actual demonstration. The top or the bottom or both may vary in position depending on where and how the surface intersects. The line string from which the component is defined is referred to as the spine. We define a string of points or line or open shape to set the geometry of the component. The top is always the top limit of the component and the bottom is always the bottom. This spine is not necessarily top, but will always be between the top and the bottom of the component depending on the properties that you set. So the top options are to follow a surface, which we talked about. Typically that's your existing ground. Follow component. And remember what I said there is typically that means to follow what you drew. So if you're building your component at 12 feet at minus 2%, to follow that. And then the third option for the top is to follow the highest of the two. So if it's the surface or the component, depending on which one you pick, that's what it will trace. And then the bottom essentially is the same scenario, except this time we have an option to also follow lowest. You'll see in the third bullet point. So follow the surface, your active defined surface. Follow the component that you drew. So it would be a depth below that top. Follow the lowest between the component bottom or the surface, or follow the highest between those two. And so what we're going to do is we're going to take a look at constructing 4 different situations typical in design. And the first one we want to do is I just simply want to trace the ground, follow the active surface at a fixed depth of 1 inch. And so you'll see our settings that the top option is going to follow the surface. The bottom option will also follow the surface. Because we're not following a component itself, then we have to give the depth to the active surface itself. And notice that's not a positive number, but it's a negative number. It's assumed because you're following the surface that it will be below the ground. So let's go in and build that component and do a quick test. So the first thing we want to do is to build this component to follow the existing ground. So I have a new template here called Nominal Depth Milling. So we'll right click, add new component, overlay stripping. We'll give it a name, overlay nominal depth milling, a feature, overlay milling, and again, this is using the examples workspace. The top and the bottom, in this case, would both follow a surface, and we'll just give it a depth. So I'll just do 1 inch and then tab and let it do the math for me. And then I can give it a parametric constraint label name. So we'll just call it milling depth. Using my dynamic settings and my apply fixes, I can do the left and right side at the same time, actually, with the mirror. And so we'll start at 0, 0. And I'm just going to go over horizontally 10 feet and a slope of 0. The slope really is irrelevant simply because it's tracing the ground. So it's not going to be following the component. And so when that terrain is applied, and we'll do the test here, I can put in a slope, for example, to my existing ground. So minus 2%. And so as I draw that, you'll see that it just follows the ground. You can, of course, make one component just from the left to the right side. Again, all we're doing is tracing the ground, so it's irrelevant in terms of how this is constructed. The point is the tracing. So let's now save this and apply this to a model. And what you can see here as I scroll through my sections, I essentially just locked in at 10 feet left and right where I'm tracing that ground. And so typically this is not the way things are done in construction, but I just wanted to show you that you can literally trace an active surface. And you'll see that the points that were essentially dropped down, you'll see those show up and come down, and then that depth is then applied. So that is how we can do a nominal depth milling component where we simply trace the active surface at a fixed depth. I did toggle on stripping so that it will be computed in the component quantities individually. The next thing we want to do is we want to take this concept of tracing the surface on the top through, but on the bottom we want to then tell it to follow the component and then assign a component depth. And the result is going to look like what you see here in the screen capture, where the milling will actually do crown correction when the component depth falls below the active surface. But when the component depth falls above the active surface, it will just trace the active surface. And so you will see here in this situation that we have milling, crown correction milling up until this point. And then once the component depth falls above ground, then we simply follow the surface along the bottom at that point. So there's no more quantity calculation, if you will, in that location. And so what we want to do then is apply these to our next template. So let's go ahead and get started making our new overlay component that is going to do milling with crown correction. So we'll select the overlay stripping, and I'll call this slope correction milling. And we will go ahead and set our feature. We use the same one here for overlay milling. And our top option is going to, again, follow the surface because we're milling. But the bottom this time, instead of following the surface, is going to follow the component. And we're going to assign a depth to the component of 2 inches. So I'll just type 2 inches tab. We're not going to be following the surface, so these settings are irrelevant. We do want that to be considered for quantities. And we can set a parametric constraint label for milling depth if we want to. And then we're going ahead and place our first point. Now I'm going to do 10 feet left down at 2% because now our slope matters. We want to do 2% milling. And so I'm going to say my first point is going to be minus 10 and minus 0.02. So that's our first point. And then our second point, which will be essentially our centerline point, we're going to give it a 0, 0, enter that, and then our last point will then be 10, 0.02 for a 2% crown. We'll finish that. Actually, I wanted that to be a minus 0.02. So we'll do that. And we can go ahead and fix our constraints here if you want to. For example, I can remove the constraints here, and then I can add a horizontal and a slope, just like you would a normal component. And then just to be consistent over here, we'll change this over to slope. And essentially it looks like a regular component, but this is a special component. It's an overlay component that's going to follow the component on the bottom. In other words, it's going to follow along the bottom what we drew. What did we draw? 10 feet at 2% in both directions, and that's what we want it to follow. And it's going to follow 2 inches below the profile grade location. So we'll go ahead and close and save that. And then what we'll do then is take a look at how that template works in our model. And you can see a good example here on this particular sample data set is the top of the component always follows the active surface, but the bottom of the component follows what we drew. So here is your 10 feet at minus 2%, and thus it gives us our variable depth milling based on the depth below the profile grade location of 2 inches. Now it's time to begin to combine what we have learned. In this next example, we want to go ahead and use our nominal depth milling that we did earlier, but we want to add a second component that essentially corrects our cross slope by filling our milling section back up with leveling binder and then taking that leveling binder all the way to the profile grade location. So you can see we have essentially two templates, or two overlay components. We have the stripping, which is following the surface for top and bottom, and then we give it that 1 inch surface depth. It is a stripping component, and we have a parametric constraint label. Then the second component we add to this, the top is going to follow what we drew, or follow component, so 10 feet at 2%. The bottom will follow the active surface, and making sure that our depth with our milling and our overlay binder are the same depth. That way we know that the bottom of the two match. And again, you can set a component depth for a parametric constraint if you want to, but in this particular situation, if I set it, I would need to set it on the surface depth because we want that bottom to be the same for the milling and the overlay. So let's go see how we construct this. So to complete this third example, I've taken the nominal depth milling template and made a copy of it and called it nominal depth milling and crown correction leveling binder. And so we're going to go in now and add this next overlay component. So we're going to add the overlay stripping component. I'll call this leveling binder, and we'll set the feature to that, to overlay leveling. The top is going to be, this time we want to follow what we draw, so the 10 feet at 2%, so we'll follow component for the top. The bottom is going to be to follow the surface, and then on the surface depth, we want it again to be the 1 inch depth. And we can, if we wish, give it a parametric constraint label, but at this point you should understand what we're doing with that. And so we're going to now place this overlay component coming off of the PGL location. And so I'm going to come in to the center, and again we're going to, if we want to use precision input, we certainly can, but we're going to come over horizontally 10 feet, and we're going to come down at minus 2%. And we'll finish. And then we can do the same thing on the other side. All of the settings are going to be set as the same. We'll change this to make sure follow component, follow surface, 1 inch depth. And again, that will be stripping. We might go check our properties over there. And this is going to be minus 10 feet. And our slope is going to be a positive 2% this time because of our signage. And we will finish that, and I'm just going to check this property, follow component for the top, follow surface, 1 inch depth. Should be the same for this, follow component, surface, and 1 inch depth. And so now if we take that template and we apply that to the roadway, we will see these results. And so if we take a look here, you can see essentially on our cross section is the easiest way to look at this. We have two components. Our first one is our nominal depth milling, and it follows the surface at the top and the bottom at a 1 inch depth. But what we've introduced now is filling that milling back up with leveling binder, where it goes to the bottom of our milling and follows that surface, but at the top it follows the component dictated by the profile grade and the width and cross slope that we assigned when we laid out the left and right edges of pavements. And so you can see we have our leveling binder component, and then we have our milling component. In this last example, and is probably one of the most common applications in today's construction industry, is to use the milling to correct the crown and then refill that location that was milled with a leveling binder substance. So in other words, crown correction milling in addition then to slope correction milling. And typically that's the way these projects are constructed. And so in this example, we're going to use two components where the milling is going to correct the crown where it can. And I say where it can because the bottom is going to be 2 inches below the top of the component. So sometimes it will be milling and sometimes it will be tracing the ground, just depending on the depth below profile. And then the leveling binder is going to then follow the lowest option on the bottom, where the top is the component, obviously, because we want the top of the leveling binder to be the proper slope. But the bottom is essentially has to fill in whatever is lowest. And so whatever is lowest is either going to be the bottom of proposed milling or it's going to be the active surface. But again, we want to be essentially 2 inches below the proposed profile, and that's where we get our component depth. And so let's go in now and construct this template to perform this final example. So to complete this template, I made a copy of the slope correction milling template that we did on our last exercise and renamed it to add the descriptor leveling binder added to this. And so to complete this, we'll right click, add a new overlay stripping component, and we'll call this leveling binder. Set the feature for that to overlay leveling binder. Overlay binder is fine, or leveling. And then we'll set our options. And so the top is going to be to follow the component, which is going to be the 2% at 10 feet. The bottom will be to then follow the lowest of either the component or the milling component. So whichever one of those. And then we want to be at a component depth of 2 inches here. And we need to make sure that that is a stripping component. And then we'll come in to accept our first location. And again, we can essentially, because they're both dealing with slopes, we can retrace our points here. And then finish. And it doesn't have a depth until it actually sees the surface. But what I do need to do on the milling is I need to change or confirm that its depth is indeed 0.167 or 2 inches, and it is. And so that's our milling. And then our leveling binder, again, has the same depth. So follow component, follow lowest, 2 inch depth. That matches up. And then on our actual milling component, which is here, that should be follow surface, follow component, not follow lowest here, but follow component, and then the same depth. Once those are set, let's go in and apply that to our project. And so taking a look at the results, you will see that we have two components, but the bottom is actually now has a corrected cross slope, which is typically the way we mill. And then the top also has the corrected cross slope, in other words, following the component. And so this gives us, again, the two different components to be able to calculate those quantities separately, making sure that you have the stripping component turned on. But both the top and the bottom are now actually following the corrected cross slope. So the milling utilizes corrected cross slope and as well as the leveling binder. And so that concludes the 4 examples in terms of how we can come up with different scenarios with our overlay. The next thing we want to take a look at is how does the optimization of the profiles take place on these particular examples. So using our template that consists of 2 components, one for crown correction milling and the other for the leveling binder that goes to the bottom of the milling and then follows the component along the top. Let's look at now adjusting the profile to optimize different design scenarios. Underneath our task and corridor modeling, there's an icon here for overlay vertical adjustment, and I have actually opened that toolbar over to here. And what we're going to do is start very simple, where I have the backbone thickness set to 0, the minimum mode is evaluating minimum overlay depth, and the minimum overlay thickness I'm going to set to 0 for our first test. And we're asked for the label for the backbone parametric and as well as the overlay parametric. Those we're just going to omit for this discussion, but essentially all they are is parametric constraint labels that you can assign in your template. And then we want to then take a look later at utilizing or limiting maximum milling and what that means and how we define our range points. So I'm going to get started here to locate the corridor. And by the way, right now it's just using the existing ground as the active profile you can see there. So we're going to locate the profile and we'll give it a name. I'll just call it overlay vertical adjustment, and I'm just going to go from beginning to end. The backbone thickness essentially does all of the calculations in terms of where to float in the overlay leveling, and then it adds whatever is set to the backbone thickness to the top of that, and so it ultimately heightens that last one. And so since we're controlling all of our heights directly in our template, we can leave that set to 0. Then we want to look at the minimum mode. We have minimum overlay and we have minimum milling. Think of minimum overlay as coming down from the top and finding the top most critical point. And in this case, it would be here in terms of the existing ground. And because we've set our minimum overlay thickness to 0, we would expect this profile to be adjusted where this white line exactly matches the highest point along that component boundary. And so we're going to do minimum overlay at a depth of 0. And then the other thing here we have to tell it is what points do we evaluate. The range point means go all the way from this point to that point, and you can pick those in your dynamic cross-section view, but I'm just moving from the left edge of pavement to the right edge of pavement. And then you can tell it how do you want to evaluate the existing ground. Do you want to evaluate it from within the template range, from existing linear geometry? For example, maybe you've picked up existing edges of pavement. Do you want to follow features, or do you want fixed offsets? Typically, I just modify or follow the template range. And then lastly, how do you want to examine the surfaces? Do you want to examine all cross-section points or just the 3 template points, left, center, and right? And I'm going to do all cross-section points. Maximum vertical difference is a final override to make sure that we haven't gone too far, and if we leave that set to 0, it'll be ignored. And so I'm going to do minimum overlay set to 0 for my first profile test. And so we'll go through the prompts here and allow that then to design a profile. And then when we set this profile active, you'll see, just as I said, that the profile is brought up, top of the leveling binder is brought up to where a minimum overlay of 0 depth is achieved. Now we can go into there and let's do one more test. I'm going to run that again. So we'll locate our corridor. But on the minimum overlay, let's change that to 1 inch. So we'll do, or I don't know, a tenth let's just say 1/10 of a foot just to keep it simple. And so we'll come in here and we'll allow that to change, process, and then we'll make this profile active. And now this distance from this topmost critical point to here is going to be measured at 0.10 feet. And so if you were to measure that, it would be what it is. And then the reason this milling goes below ground is because you've set a depth below component of 2 inches in your template, and so it follows that component as expected. And so you have a section here of actual milling, but over here there is no milling. Your leveling binder is just going to your existing ground. So that's one method of profile adjustment design. So let's do another one here. Take a look. So the next one we're going to do, instead of minimum overlay, we're going to do minimum milling. And I'm going to just leave all the defaults, and I want you to see the difference. And so we'll locate our corridor, and we'll go through the prompts again, this time doing minimum milling. And now we want to think of it as coming from the bottom up to the lowest critical point. And so we're going to set this profile active, and you can see it would come from the bottom up. The lowest critical point actually fell over here on the right side. So minimum milling gives us now, this is our milling configuration, and all then of our overlay, our new component, is down here below ground. So we're actually cutting all of this out, which is not practical, but it's a good demonstration of the point that we're trying to make here. All right, so let's take this back to existing ground, and we'll come in and do another test here. Now what we're going to do is we're going to keep the minimum milling set here, and just to show you then how backbone thickness works. Let's say that our backbone thickness is 0.5. It's just going to add to whatever it solved another 6 inches on the leveling. And so we'll pick our corridor and we'll go through the prompts real quickly here. Let it design that profile, and it just, whatever it comes up with the profile, it just adds the backbone thickness to it. And so now you'll see that's a solution that we get. And it's just kind of important to understand, you know, the different parameters. So we added so much to it, it doesn't need to mill anything. This is all just going to be leveling binder in that case. So we'll go back and set our ground active, and I'm going to delete this one. I guess the other thing to point out here is that on the way that you design your templates, there are a couple of different ways that you can do that. Here's another example where all we did here on the top is we literally just made a regular component. It's not an overlay component, and we gave it a thickness representing something like a surface course. And then on the bottom component, what we did there on our leveling is we said top follows component, bottom follows surface. Okay, and then everything is set to 0. And so if we use this test template, and what that's going to do, even though the template itself only had a thickness on that top component, which was just a regular component, it also gives us a thickness of this quantity down here for milling and overlay. And the problem, I guess, with this approach, though, you can see that we didn't have any calculation for milling in this area based on our settings. So the point that I want to make here is you certainly can, deal with these profiles a lot of different ways. Let me go back and set this to the existing ground. But just keep in mind, depending on how you set things up, is going to give you those different types of results. My personal preferences are to utilize the depths in my template and then adjust the profile, but you may also find it equally or even easier to understand if you don't set your thicknesses in here for your overlay components and then let the profile adjustment tool do that for you. So just a couple of different approaches on that profile adjustment tool, but ultimately it's optimizing either the amount of overlay or the amount of milling that you want to utilize on your particular project. And then lastly, as you're making these adjustments to your overlay components and to your profiles, one of the things that you'll want to become familiar with is on your corridor here, on the corridor reports. If you go to corridor component quantities is one report you can look at. You also have a milling report. And so let me go back and change the template drop here. We'll grab that. So I'm going to change back to the one we were working on, which was that one. And if we come back now to our corridor and go to our reports, if I go to the milling report, you can see the left and right offset and the amount of the elevation. So the left offset minus 10, the right offset, and what those elevations are. And so you can see there the planar area that's calculated, so that's kind of handy. And then the other report that you might want to take a look at here are the actual component or quarter component quantities. And in here you'll see your leveling quantity and your milling quantities. And as you adjust those profiles, you can come back into here and look at those and put in some unit cost and determine how optimal you are on your particular profile design. And so the last thing is just remember that this profile adjustment tool is literally making a chorded profile, which may or may not be desirable, and you may want to come in and design your own profile using that adjusted profile as a guide. So hopefully this helps you with the understanding of overlay components and also in conjunction with the profile adjustment tool. There's almost an infinite possibility of ways to solve this, but with the power that we give you, I think you'll find that optimizing an overlay job is going to be something that becomes fairly intuitive after a little practice.